Hey there, my name is Seth Juarez. We're at the 2015 Microsoft Research Faculty Summit, and I'm here with two of our researchers. So tell us about the project you're working on.
We were looking at a bunch of different phone applications, and we noticed they're all reading the sensors, and the sensors have a lot of noise in them. And we wanted to make devices like the band and your phone more energy efficient, and we realized there was no way to trade off accuracy or efficiency for quality of service because there was no way to express it in any of these languages. And then we realized not only sensors have this problem, but machine learning algorithms are producing approximate answers, and also approximate computing is a new mechanism for reducing computation to gain energy efficiency, and it also fell in this paradigm. So then we're like, we need to start with the programming language abstractions before we can build systems that reason about this in a principled way.
So let's start with the actual sensor reading and why it's inefficient. So we're talking about GPS specifically. Why is GPS so inefficient when it comes to battery life?
So what happens with GPS is when it needs to contact a lot of satellites, right? And the more satellites you get, the more accurate it is.
Right.
So that takes time because you're communicating over a noisy channel to many different satellites. And it takes time just to communicate, and do the triangulation itself, right? So the process is just very energy hungry on your actual device.
There's also a notion of uncertainty with these types of reading, isn't there?
So when the GPS takes a reading, there's some number of satellites that are communicating it. Each of them has a sense of what time it is, and then there's a delay. They have very accurate clocks, but then it arrives at your phone at different times. And so it can be cloudy, a building can be occluding one of the satellites, and so when that happens, the GPS gets more and more inaccurate. And everyone's had their car GPS tell them that they're driving in a field or in an ocean, and so that's a case where the GPS can't produce an accurate reading. And right now, when you code one of these applications, like a navigation application, you essentially ignore that data and try to put yourself on a road, but even if you use good heuristics for getting yourself back on the highway and out of the ocean, what happens is it's all hand-coded and not principled. So we trying to provide an abstraction that reasons about the error in these readings explicitly and makes it easy for programmers to combine domain knowledge such as roads, the speed you're traveling, and the likelihood that your phone is in the ocean, which could happen if you step onto a boat, but is unlikely if the GPS is installed in your car.
So you're modeling this uncertainty while at the same time trying to lessen the toll on the actual battery. So is there a way to actually know where you are without necessarily having to ask GPS? Location
is a pretty abstract concept that many operating systems would like to provide, right? And GPS is just a mechanism to estimate your location, right? But there are many other ways, and in fact there are many researchers who spend a lot of time thinking of very clever ways to estimate location. For instance, you can use your Wi-Fi to try and estimate, hey, I'm in a building that I recognize, I've been in this building before. Or maybe I just use the accelerometer on the device. I took a GPS reading, say 5 minutes ago. The accelerometer tells me that the phone has probably not moved much, so I'm pretty likely to be where I was before. But you'll notice I use the word likely. So there is this notion of distribution associated with all of these types of estimates, right? And so that's what we're trying to capture in the programming abstraction, where we don't want the programmer to really have to reason about what that distribution is, right? We want the operating system to provide an abstract location service. An error is encapsulated with those particular types of ways that we would estimate location.
So we keep talking about abstraction and programmer using the abstraction. What does this abstraction look like that you've been working on?
For example, the GPS error, although what they draw on your phone is a dot in a circle, it's actually a donut. So the donut around the point they draw is, and there's a little circle, inner circle on the donut, which is where you're most likely to be. All right. So the donut distribution is called a Raleigh distribution. So you can take samples from there that describe the error, and those are other locations you're likely to be. And then when you make a decision, like to draw a point on a graph, or to compute how long you've been running, then you want to say, how likely is it that I've been that I want to draw it on this road. And then you can explicitly reason about the fact that, hey, this point is very accurate according to the GPS, so I can trust it, or it's not accurate, and so I want to maybe add domain knowledge like the road, where the road is, and move the point to snap to the road. So you just have a simple conditional that says what to do when you want to add some domain knowledge.
So you mentioned to me earlier that you were language researchers. Are you adding types or language features that will enable this type of uncertainty to be modeled well?
Yeah, we have a generic type in C#, and in fact, everything is in, it's a library in C#, our uncertainty library. And so I think it's best explained with again, a GPS example, right? So suppose that I want to compute how fast I'm going, my speed, using two GPS samples, one GPS sample taken at time t0 and another one taken at time t1. I would take those two GPS locations, compute the distance, and then use your distance equals rate times time to compute my rate. So what we do, rate is in that program that I just described, rate is a float or a double, right? But what we're going to provide is, because we're going to give an abstraction over location as an uncertain location, and we've done the appropriate operator overloading in our types, so that you compute actually an uncertain float for your rate, right? And so as a consequence, whenever you want to now act on that data, for instance, use it in a conditional to say whether or not if my speed is greater than 5 miles an hour, I might want to, post something to the user's display. That speed greater than 5 miles an hour, we use implicit type conversions to actually do a hypothesis test and try and statistically evaluate whether or not we have enough evidence to prove whether or not you're going faster than 5 miles an hour. And so our runtime, so we have a library that lets a programmer express this, and then a runtime that implements that semantics.
That's awesome. So as researchers, what's the future of this kind of research? What are you guys doing in the future with this stuff?
So I think there's a lot of challenges. This idea of domain knowledge composition, I think, is a very general principle. A lot of times, much like when you produce a library, you don't know, you make a certain surface of API calls that people can use. And depending on how a particular client uses that surface, you can do a lot of optimizations. And I think the same thing goes to be said with this idea of uncertainty, right? I mean, again, going back to GPS abstraction, people use that location service in various different ways, and coming up with really efficient ways to encode that domain knowledge of how they're actually using that, and then make the actual, what amounts to probabilistic inference faster. Because under the hood, we're really doing probabilistic inference, which is a generally very hard problem.
Yeah.
And so we need to come up with smart ways to take what the programmer knows about their domain and help hopefully come up with faster and efficient implementations of that probabilistic inference.
But more and more application programmers are dealing with estimated values. They're consuming the Bing search results. They're consuming machine learning algorithms. They're consuming sensors. So if they have to have a PhD in statistics in order to correctly build applications with these estimated values, either they're going to produce junk because they're not going to do it at all because they're going to just give up and treat them as if they're facts, or it's going to be an arduous process, and you're going to always have to have a statistics PhD on your application building team. And so what we're trying to do is provide some abstractions where we bury the complications that we've been talking about in the runtime and the programming language implementation, but the abstractions that the programmer gets to use, even though we probably could have done a better job making them seem straightforward, are actually a lot more straightforward than anything they could do. And then we want to embed them in languages like C#, Java, C++, because then they can be widely applicable in application languages that lots of people are using today. Because right now, there are some approaches that have similar goals as we do in terms of representing uncertainty, but called probabilistic programming languages. But we kind of just are a subset of that is also programmable for average programmers, rather than requiring both a PhD in statistics and machine learning.
Well, thanks so much for spending some time with us. Thanks for watching, and we'll catch you next time. Take care.